Hello, and thanks for using TickBoom. In this video, I'm going to work through the first of 6 questions that all relate to calculating volumes using calculus. So the idea, one of the applications that we can do with calculus is to rotate curves around axes and then use integration to find volumes. That's one of the really powerful applications of calculus. And there's a few techniques we can use. We can use something called slices, or we can use something called cylindrical shells. And there are 2 different ways that you can do this application. And the 6 questions that I've been sent through kind of work through, I guess, problems that take a look at both of these techniques and how they compare and contrast. So what I'll do is I'll work through each question one at a time in separate videos and then link them all up so that you can work through all of them if you want to. I think the questions have been quite well written, and they really build upon each other to really give you a deep understanding of what's going on when you use these 2 techniques. So in this video, I'll work through question 1. And question 1 says the region bounded by y equals a squared minus x squared and the lines y equals a squared and x equals a, that region is rotated around the y-axis. Use your value of a to find the volume of the solid formed. And just as background, a here is just a constant. And what I'll do is I'll just work through the solution keeping a in general terms, and then in theory students could be given certain values of a to then see what the actual value is that they get. But I'll just keep things generic for how I work through it. So I think the first natural step with all of these questions is always just to start with a diagram. So I'll just draw up a set of axes. So we've got a Cartesian plane here, and we've just got the x and y axes as normal. Where the 3 curves we're dealing with are y is equal to a squared minus x squared, y is equal to a squared, and then x is equal to a. So let's just draw those on. So I might just define this as a squared, whatever that value happens to be. So this line here would be y is equal to a squared. Maybe I'll just define this as a, so that this vertical line here would represent x is equal to a. And then for y is equal to a squared minus x squared, a again is just a constant. So this is really a, it's going to be parabolic facing down. And to kind of see how it plots, you can just take key points. So when x is 0, y would be a squared. And when x is a, y would be a squared minus a squared is 0. And then we can kind of fill in the gap. Now the key, I think the first mistake that a student could make is to mix up what area is being rotated. So we know we're rotating around the y-axis, but we're told it's the area bounded by these 3 curves, and that's this area here. So the first, I guess, mistake to try and avoid is to realize it's not this area, it's this area. And the way we can then think about the volume, we can use the method of slices here. And we actually kind of can just do it twice. We could start by finding the volume of this area here with slices, so thinking about slices and rotating them around. And then we could do the volume of all the way up to x is equal to a using those slices. And then know that the difference between those 2 volumes must be the bit that we're concerned with. So the idea of this method of slices is that if you were to take ever like decreasing slices, thinking of slices that are as small as possible, if you were to rotate those around the y-axis in this case, it can work for x or y, but here we're focused on y. you'd effectively get a cylinder. We'll kind of, maybe if I just draw it over here, like if I think of this red one, rotating that around the y-axis, it takes a bit of visualization, but you'd effectively get what looks like a coin, really. Which means that in terms of its shape, it's actually a cylinder, a kind of thin cylinder. That's effectively what a coin is. And in terms of the volume, well, the volume of that coin is going to be the area of the base times the height. The area of a circle we know is pi r squared. And in this case, if we're rotating this all the way around, the radius is essentially just the x value. And in our case, in this case here, the x value would be a. So it would be pi a squared. And h here, we can just define as the change in y. It's some change in y that we want to get really, really small. And then the idea is if you add all those up between the y values that you're concerned with, you'd effectively get the volume of the entire thing being rotated. And it's the same idea with this blue strip. So what we can do, kind of using that technique, we can say that the volume we're concerned with will be equal to, and here we're kind of in calculus territory, because by adding things up and having something get smaller and smaller, we're in integration territory. That is effectively what you'll learn is the essence of integration. The kind of integral symbol is essentially a kind of S. It's a kind of funny looking S for sum, because that's what we're doing. So here, if I look first at the rotating the vertical line x is equal to a, we're doing it between y is equal to 0 and a squared. They're the y values that we're concerned with. The thing that we're adding up, in this case, will be pi a squared dy. So that's going to give us this volume rotated around, and then we want to subtract from that the volume of this curve a squared minus x squared, and that's then going to give us what's left in between. So again, for rotating these strips around, it's the same thing. We're still going to be integrating, still between 0 and a squared. Now we need to think about what would the, I guess, volume of each strip be for this curve. And it's the same idea, area times height. The height is still going to be dy, but the area this time would be pi. It's going to be effectively the radius of each of these, I guess, coins or cylinders will be the x value of this function, and then the area is pi r squared or pi x squared. So we want to write x squared here, but because we know we're integrating with respect to y, it would be helpful to put x squared in terms of y. So we can do a simple rearrangement here. So if I bring the x squared and y over, we'd get x squared equals a squared minus y. And so we want to then substitute this x squared in, but do it in terms of y so that we can integrate with respect to y. So this would be a squared minus y, and then dy for the height. So that's the basic setup of using this technique to find the volume. From here, it's just integration. So we need to just use our rules of integration to eventually get the result. So I think the hard work's been done in visualizing and working out what we're really dealing with. Now it's just the mechanical process of integration. So I'll just work through it, keeping a as a variable, and then in theory you just substitute your value of a to kind of get a final answer. So if I think about integrating this first bit, we can bring the pi out and the a squared out actually, because they're both constants. So we'll get pi a squared, and then really we're just integrating 1 dy, and the integral of 1 with respect to y would just be y, and that would be between 0 and a squared. For the second integral, we can bring out pi. I'll just bring out the pi. And what we're left with inside the integrand is a squared minus y. The integral of a squared would be a squared y. Remembering a is just constant. The integral of y would be, so minus y would be minus y squared on 2. So we just add 1 to the power and divide by the new power. So very, very simple integration here for this first question. And now we just need to kind of work through. So we'll have pi a squared. So we'll go a squared minus 0. That's just inserting the upper and lower boundaries, minus pi. And then if we do a squared, so a squared times a squared would be a to the power of 4 minus a to the power of 4 on 2. And then minus 0 minus 0. So that's just going to be 0. So we'll get pi a squared times a squared would be pi a to the 4 minus, and we've got a to the 4 minus a to the 4 on 2. So we've got a to the 4 minus a half a to the 4 would be a half a to the 4. And then we've got multiplied by pi, so minus pi a to the 4 on 2. And now we're left with, again, a to the 4 minus a to the 4 on 2 with a pi outside. So that's just going to be a half left. So equals pi a to the 4 on 2. And then always remembering units. We're not told a specific set of units here, so I'll just write it in general units cubed.
Panic boom!
All right, and that's that first question. So we've used slices here as a technique. I mean, in theory, we could have used cylindrical shells as well, but the technique of slices resulted in such simple integration that there's no real need to, try an alternative. What we'll see as I work through the other questions in this set of questions is that what it's really trying, what the question writer is really trying to get us to appreciate is that sometimes using slices is a good idea and sometimes using shells is a good idea. And as you get more comfortable with both techniques, you can build up this kind of intuition to kind of work out, well, which technique will be better for me in certain circumstances. And that intuition really just comes with practice. There's no real shortcut to that. But the key is to have both tools in your toolkit. And kind of in the context of the higher school certificate in New South Wales, this technique here of slices you would learn if you were doing the 3-unit course or extension 1. And then cylindrical shells, I believe, comes in at the 4-unit or extension 2. So kind of for 4-unit students, you kind of will end up with both of these tools, but for 3-unit, you'll kind of stop at slices, and perhaps if you did some further study at university, you'd probably learn cylindrical shells as well. So hopefully that all made sense. If you found that explanation helpful, please be sure to give it a like. If you're someone who wants to keep your finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. All right, tick boom.